Okay, this is lecture 4, and we're going to start our discussion of pumps here. And in this lecture, we're going to talk about classification of pumps. We're going to briefly touch on dimensional analysis so we can get at this issue of the affinity laws for pumps, and we'll use that a little bit. And then we're going to get into specific speed. This is all about picking your pump. In this particular lecture, we're going to only touch the surface in some areas in terms of classification. This is not a lot of heavy detailed computation in lecture 4. We're going to get into that in later lectures when we talk about designing and selecting a particular pump based on a pump head curve and a system curve. But these are things that are important to understand as well. So there are some computations, so you should definitely work the lecture assignment problems. If we think about pumps, we want to do some definitions here and kind of set the stage. They're hydraulic machines. They convert mechanical energy into fluid energy. We mainly classify them into two major categories. You've got deposit displacement pumps. Screw pumps fit into this this particular category. Think of this as where you are actually displacing the fluid by some sort of a piston or a screw. That's in contrast with a rotodynamic or kinetic pump, where we actually accelerate the fluid by some sort of impeller system. The positive displacement pumps deliver a fixed quantity of fluid with each revolution of the pump motor, such as with a piston or cylinder. The rotodynamic pumps add energy to fluid by accelerating it through the action of a rotating impeller, just as I said. These rotodynamic pumps are far more common. You see those in a lot of applications. And of the rotodynamic pumps, we've got three major categories, and this is where the specific speed later is going to come into play as to which one is the most efficient for a particular application. And that's what we call radial flow pumps or centrifugal pumps, axial flow pumps, or mixed flow pumps. I want to note that this is the European classification. A lot of the US textbooks put all three of these into the category of centrifugal pumps, but that's not exactly matches the European definition. This is just a flow chart showing you the kind of the classification of the pumps and where we get into the positive displacement. Here we're calling them kinetic pumps. You'll note that before we called it rotodynamic pumps. Here we're calling it kinetic pumps in this particular publication out of Garbus's a paper. And so you can see the various types of flow pump characterizations here based on this particular graph. In these photos, you'll see two different types of major pump categories. We've got a positive displacement screw pump here in the upper, where we're actually lifting by means of the screw pump. You're lifting the fluid up through the system. Here is a large scale rotodynamic. These are actual axial flow pumps, which we'll explain a little bit more about those in a second. There's some advantages to positive displacement pumps. You can pump large solids without clogging, and you can operate at a constant speed over a wide range of flows at pretty good efficiencies. This is looking at the differences between axial flow and radial flow pumps. At the top here, we have a radial flow pump, and you can see that the impeller is spinning. And what it's doing is, as the water comes in, or the fluid comes in, it is actually accelerating that fluid by throwing it out along the radius. So it's spinning it in a direction, and that's why we call it radial flow pumps. And as it's accelerating, it's spinning it, and it gets ejected out the other end. And so that's a radial flow pump. An axial flow pump, as the flow comes in, the impeller is rotating along the same axis as the flow. So whereas the impeller rotation axis is perpendicular to the flow in a radial flow pump, the impeller is rotating on the axis of the impeller rotation is on the same parallel track as the flow. And so you can think of this more like a boat propeller, as you know, you're propelling a boat you've got on the back of a motor on the boat. That's a propeller. We call it an impeller in the pump kind of scenario, but as it's rotating and accelerating the fluid through it. And so these are going to basically be different kinds of efficiencies based on the kind of flow, the head, and all the things that you're going to encounter in your application. You're going to pick one radial pump over an axial flow pump for different circumstances and vice versa. We'll talk more about that in a second when we get into as I mentioned, specific speed. A mixed flow pump is a pump that where the axis of flow and the way that the impeller is set up, that it's not truly parallel to the flow, and it's not truly perpendicular flow. It's a mixed setup there. This is a picture of a centrifugal pump or a radial flow pump. You can see as the flow is coming through the system here, it's coming in and then it's being spun up as it enters, and it's being thrown radially around here as it's sped up and injected into this pipe here, the discharge line. This is just another set of graphics here that kind of demonstrate this business of radial flow versus axial flow. So here's an axial flow here, here's a radial flow here, and then you've got this mixed flow, which is kind of a mixture of axial flow and radial flow. There's a number of things that have to go into pump design, and so I'm just going to mention a few things here that you're going to see. This is a look at a graphic of a pump, and so we've got the pump sitting right here, and we've got the intake line here, the intake side of the pump, and you'll notice here that it's submerged into the water. You've got some sort of strainer here to keep out particles that could foul the pump. And you'll notice here we've got listed this foot valve, and the foot valve is sitting there to when the pump shuts off, it doesn't allow water to evacuate back out of the line, and so it's keeping the fluid right on the eye of the pump impeller even when it's not running. If this foot valve is not in place, this can drain out, and then I've got air in this intake line, and so your pump is not going to work very efficiently until it becomes what we call primed, and so that's a very inefficient process and can cause damage to the pump and things like that. So we install these foot valves on the intakes to keep water or whatever the fluid you're pumping to evacuate back out the other way. So these are some other types of valves. We've got the check valves. We're not going to get into valve design, but I'm just kind of mentioning these kind of things. So the check valve would basically be able to prevent backflow. So you don't want water or fluid going back the wrong way. And so they're designed such that you can have a check valve where it checks the flow. It allows it to go one direction, but not the other. You also have additional valves. You have gate valves and other kinds of things that you'll have to deal with when you design these systems. If we think about pumps, we know we've got things called single stage and multi-stage, and all these are, a single stage has one pump impeller, where a multi-stage has multiple pump impellers. And when you have these multi-stage pumps, you can actually kick on the various parts of the impellers, and what they're there for is to add additional head to the system. Remember, when you have a series of impellers or pumps in series, they're not going to add additional flow, because the least common denominator, the pump that, whatever goes through one impeller is the same flow that's going to go through the next. There's a sort of not a restriction there, but you've got the pump that has the impeller that has the least amount of ability to push water is going to be the least common denominator. If you wanted to add additional flow, you would put pumps in parallel, not in series. So a few key things to think about here. Multi-stage pumps, two or more impellers are arranged in a series such that the discharge from one impeller enters the eye of the next impeller. If a pump has 3 impellers, we call it a 3-stage pump. Multi-stage pumps are typically used when pumping large heads and commonly used when extracting water from deep underground sources. So if you're going, from quite a ways deep to push out, you're going to have to have quite a bit of ability to inject a lot of head into that system. The next thing we're going to talk about is this idea of efficiency. And when we talk about pump efficiency, we're going to talk about the power delivered to the fluid. This would be the H sub P in our nomenclature, divided by the power supplied to the pump, to the shaft. So this is, what's required from the electrical company. For example, how many kilowatts does it take to run that pump? And then how much power do you have delivered to that pump? And I said this is H sub P, so it's going to be rho, gamma, Q, H sub P. That would actually be the definition of power. We'll get a little bit farther into that in a second. The last thing I want to talk about on this particular page is the concept of homologous pumps. And that means we have geometric similarity. And so when you see a pump head curve, usually you'll see multiple curves. And that means these are multiple types of pumps, but they're all homologous or geometrically similar. And so when we talk about geometric similarity, we're thinking of things are scalable and they stay within scale. So if you think of scaling a human being down to a doll, we have geometric similarity there in that the head scales with the arms and the legs to make it look proportionate to what the actual person looks like. And the same thing with pumps. When we scale, we have geometric similarity to pumps. All the components of the pumps and all the different length scales are going to stay proportionally as you scale up and you scale down. One thing I've left off here, and I kind of mentioned it here, but we've got head added to the pump. We're going to symbolize that by H sub P. That should be familiar with you to you from fluid mechanics, where you did pipe flow problems, and sometimes you actually talked about pump head entered into the system. So some basic terms, we've got pump capacity, and that's going to be the discharge of the pump. And remember, the pump can put out various discharges, but that's going to vary based on the head that it has to pump against. And so we're going to talk a lot about that. The pump head, again, is this H sub P. That's the head added by the pump. The efficiency is either going to be abbreviated nu, or sometimes we'll have it as E, and that's the power delivered by the pump to the water divided by the power delivered to the pump. And that's the, this is what does it take to run that pump to push that amount of water through and that amount of head that you're added in. And again, we've got the homologous series of pumps, geometrically similar. So just kind of reinforcing some of the basic terms. This is a graphic that kind of shows kind of a pump setup. I've got this reservoir down here, and it's at some elevation, and I'm going to pump it up to this upper reservoir of a different elevation. And in the middle here, I've got this pump. And so I've got different things here, just kind of getting you kind of used to this. You can see that the total head here, you've got some losses due to entrance into this pipe. So you've got some head losses there. Then we got further head losses due to friction up to the pump. And then once we get to the pump, we add in a whole bunch of head due to the pump head that's entered in. So this is the H sub P. And then as we move over to this reservoir, we have losses going through here from maybe the losses due, the minor losses to the gate valves. The bigger loss is going to be the friction loss. That's the water going through this pipe. If we look at dimensional analysis of the pump, so let me close this with saying we're going to deal a whole lot more in subsequent lectures when we look at these kinds of systems, and we will develop what's called a system head curve. And so you're going to see this graphic again. So let's switch gears a little bit. Let's say that I was going to be doing a laboratory experiment where I was going to be testing a whole bunch of different pumps. And so I'm not sure that you covered it in fluid mechanics, but we do something called dimensional analysis whenever we're doing laboratory experiments, and we do this to get at what are the major parameters that we need to collect when we're experimenting on a particular apparatus, or we're trying to understand a particular phenomena. And so we would list all the potential things that we could experiment on, or what might be important to the process. And if we look at pumps, we've got various things that we're looking at here, where we look at, okay, we're going to be definitely looking at the head that's added by the pump, and some of the factors that might be important. You know, you've got acceleration of gravity is always a good one to put in there. Things about the fluid, like density of the fluid, dynamic viscosity of the fluid. Well, then we've got the diameter of the pump head, you know, the pump impeller, what that diameter of the pump is there. What is the speed that the pump is turning in terms of how fast is it's spinning, you know, the impeller. And then we've got the flow that's being put. So if these are all the potential parameters that we could be collecting in the laboratory, let's try to combine those in a way that gives us some non-dimensional terms that might be able to help us understand the phenomena, because we're going to be testing various diameters, various flow rates, various speeds of the pump. And if we want to try to plot this data, we want to be able to plot it such that it fits in a non-dimensional sense, that no matter what kind of data we've got, we would like to see that relationship all plot on one curve. And so we do this thing called the Buckingham Pi theorem, and we combine the dimensionless terms, or we combine the parameters that we have into dimensionless terms. And so using a Buckingham Pi theorem for pumps, we're able to do this. And I've got lectures 21 and 22 in my old fluid mechanics lectures. I haven't taught fluids in several years now, but I used to go through this and kind of talk about how to do this. And so I can give you those lectures if you're interested. But this is what we'd end up with dimensionless terms, where if you look at this, this is the acceleration of gravity, this is the head of the pump, this is the diameter of the pump, this is the speed of the pump. If you look at the terms here, the dimensions on acceleration of gravity, which is length per time squared, the dimensions on the head, which is in length, and then we've got length squared here. And let's see, I think it gets us, this is a revolutions per time, so this has got time squared down here. We can combine that, we can say that that fits against, it's a function of, if I've got flow rate, which is length per time, or length cubed per time, I've got speed of the pump, which is revolutions per time, and then I've got diameter of the pump, which is in length cubed. This makes this dimensionless. This is now my diameter. This is my dynamic viscosity. This is my speed. This is my density of the fluid. These are all non-dimensional or dimensionless aspects. This is a term here that's dominated because of the dynamic viscosity. We think of that as a viscous type of term. And so if we've got kind of a thick fluid, maybe thinking of pumping ketchup or maybe mud, viscosity of the fluid plays a big role. But for most applications, when we have water, we can ignore the effect of the viscous terms, and we end up for pumps just having these two parameters being important to us from a laboratory experiment. And so if we go through and we plotted all the data points of this term here, which is the dimensionless head term, and this is a dimensionless flow term. We're going to give this terms here in a second, but we could plot all that data, and it would fall pretty much, if these are homologous or dimensionally geometrically similar pumps, they would plot pretty much on top of each other. And in those, we would also plot the efficiency. So the efficiency, remember, the efficiency is the amount of head imparted into the flow by the pump divided by the amount of power or head or energy that it took to get the pump to run. If we look at a plot of that efficiency, wherever that's a peak is where we want to be, because that's costing our client the least amount of money to operate the pump. And so we want to be at this peak efficiency point. And so at this peak efficiency point, we have this these points that also plot on this, and we're going to look and see what are these in terms of K2 and K1, this best efficiency point. And so since we want to get this, we want to look at the best efficiency point. Typically, that's on the nameplate of the pump that you're looking at, where it operates at the best efficiency. It'll give you the head and the pump flow rate that it happens on. But we're going to look at these characteristics of the K1 and K2, and we're going to call this one in terms of the dimensionless flow value. We're going to call that the discharge coefficient, and the dimensionless one that has to do with head, we're going to call that the head coefficient. And so we're looking at where these are most efficient, and that was in this location here where we had the highest efficiency point. And we can plot a whole bunch of that data, and we can say that at those points, we're going to look at that from a specific speed standpoint, which we're going to get to in a second. But as we look at these discharge coefficients and head coefficients, which are again dimensionless terms, we're going to now say, let's develop something called the affinity laws. And these affinity laws help us in that if we look at two geometrically similar pumps, if I've got the discharge coefficient for one pump and the discharge coefficient for another pump, these should equal each other, because again, these are dimensionless, and if they're homologous, no matter where you're at, you should be able to say for pump one, if I've got a discharge coefficient, that's the same thing as for a different pump. And so it's all in how these components of the discharge coefficient fit together. And so if I know the flow rate for pump one, and I know the diameter and the speed, I can look and say, okay, if I keep the flow rate the same, but I want to operate at a different speed, what's going to be the diameter that has to be that pump? Or conversely, if I know the flow rate for pump one and I've got a diameter and a speed, and then I say, well, let's use the same diameter pump and let's change the speed, what's going to be the flow rate? That's how we use these affinity laws. So this is from the discharge coefficient. If I look at the head coefficient side of things, this is what I look at. These affinity laws state that the head divided by the speed of the pump squared times the diameter of the pump squared, that for pump one is equal to pump two. So these are the two main affinity laws, and then you can get them for the same thing for the power. And we're going to use these affinity laws, as I said, very simply. If I've got one pump and I want to change maybe the speed of that pump, I can tell myself, or I can solve for what is going to be the flow rate. If I've got the same diameter pump, notice the diameter is here on both sides of these equations. If I know that I've got the same diameter, these affinity laws become very simple, where I can relate the head of pump one to the head of pump two based on the speed of pump one, the speed of pump two squared. Same thing for the flow of pump one. The flow of pump two is related to the speed of pump one and speed of pump two. And then the power of pump one versus pump two related to the speed of pump one and pump two. So we're going to work an example problem separately here, but we'll move on, and it'll be basically using the affinity laws to solve for that. So I want to move back to where we were talking about specific speed, and this is really kind of a very cookbook type of approach. As I mentioned to you, we look at this best efficiency point and we get this value of K1 and K2, and again we've plotted the head coefficient versus the discharge coefficient here. And if we do a series of examinations of this K1 and K2, we can call this, if we look for these points where they're best efficient, we can call the ratio of those the specific speed. And so we calculate the specific speed, and again, this is in SI units, where the speed of the speed is in revolutions per minute. The Q, I think, is in cubic meters per second. I have to look at chapter 2 in the Chin supplemental notes that I gave you in the module. I'm pretty sure that's in cubic meters per second. And then the head is going to be in meters. Acceleration of gravity is in meters per second squared. And if you compute this and you go to a particular graphic, you can see this will help you select which type of pump is most efficient. So if I've got a specific speed that I computed on that previous equation, and it's between 0.15 and 1.5, then I'm going to select a centrifugal or a radial flow pump. If it's greater than that, I might be in the mixed flow range, or if it's well above that, it's going to be the axial flow. Again, that's using this equation here, which is equation 2.112 in the supplemental notes I gave you out of chapter 2 from Chin. And so if you want to stick with English units, in the United States, a lot of times you'll see specific speed, which I've got abbreviated here as capital N sub S. They don't have the acceleration of gravity down here. It's eliminated. They simply don't worry about dimensional consistency to make this an actual non-dimensional term. They've got the speed of the pump, the flow rate in gallons per minute, and the head of the pump in feet. This is what you're going to see mostly in most of the American design manuals and in design handbooks, is the US form of that. If you look at this graph that is put out by Mays, which I think is, I'm not sure where he actually got this, but it's likely comes from a design manual. You can see that here is the capital N sub S in the US customary units. And so if you're on the lower end, again, you're looking at a radial flow pump. If you get on the upper end, you're looking at a axial flow pump. If you're in the middle, you're at this mixed flow category. So if I'm looking at, calculating a specific speed like of 600 to 1,000, well, I'm going to be in this radial flow end of things down here. If I'm up around 5 to 10,000 for a specific speed, then I'm in the axial flow. Again, I'm in the middle here. And you'll note that they have, in this particular graph, you can use SI units in this form, in the English form here, and you can see they've made a conversion. And so these are numbers that are quite a bit higher than what you would see if you're actually using the European version of specific speed. And so I just kind of make a note of that here in this, where you're aware of that in the graph. Okay, so axial flow pumps, generally when you're talking about where they are most efficient, is where you've got large flows and small heads. So this is a shot of an axial flow pump system down in the Florida Everglades, where you've got a head maybe of 5 to 10 feet, but you're pumping hundreds of cubic feet per second, or several thousands of gallons per minute of water. This is just another shot of this same thing in the South Florida Water Management District. Okay, I'm going to work the example problem in a separate recording.